When we want to derive a general formula in mathematics, it's not enough to derive the formula for a couple of concrete values in the real numbers. We usually have to use general variables to represent values in the function, and this is so that we can prove the result in general or for all values in the domain at the same time. Remember, you cannot plug in all of the real numbers into a function and check the details, or into a formula and check the details, because there are infinitely many real numbers and it would take you an infinite amount of time to check each one individually. So this means we have to be able to evaluate our function at some combination of abstract values, say a and a plus h. And there's a particular combination shown here, f of a plus h minus f of a over h. And this is called the difference quotient. And this is very, very important in calculus. And it's very important to be able to calculate this combination for any given function f. So let's try some examples. Let's look at f of x equals x squared plus 2, and let a stand for any real number. Now, a is a placeholder for any real number. However, we're not going to substitute any particular real number for it. We're just going to calculate f of a. You can think of perhaps a in the same way as a lot of people think of pi. Pi is a real number, but on the other hand, people think more of the symbol pi than the number itself when they're calculating. So in this case, f of pi would be pi squared plus 2. Now pi is a concrete number, but we have to write the result here in terms of pi, because pi is not something we can write down with finitely many decimal places. And in the same way, a is any real number, and whatever it might be, f of a is a squared plus 2. That is, when I substitute a for x, then the formula tells me that f of a is a squared plus 2. What about negative a? Well, when I put in negative a instead of x here, when x is negative a, then f of a is negative a squared plus 2. Now, of course, negative a squared is a squared, so I can just write a squared plus 2. So in fact, that's the same thing as f of a. F of a squared, well, what's that? I've replaced x here by a squared, so I must replace the x in the formula by a squared to get the result, or to get what it actually equals, and I get a squared squared plus 2. And now the rest are details. A squared squared is a to the 4 plus 2, and that's my answer for f of a squared. What about f of a plus h? Well, now I've replaced x by a plus h, so I must replace every x in the formula by a plus h, and f of a plus h is a plus h squared plus 2. Now I can expand that. It's a squared plus 2ah plus h squared plus 2. What about f of a plus h minus f of a over h? Well, that's equal to a plus h squared plus 2, that's f of a plus h, minus f of a, which is equal to a squared plus 2 all over h. So you see, I'm just filling in details here. This is f of a, and this part here is f of a plus h, and this is the h in the denominator. Now I can expand that a little. That's a squared plus 2ah plus h squared plus 2, that's expanding f of a plus h, minus a squared plus 2 all over h. And you see I can tidy that up quite a bit because I have some cancellation here. It's a squared plus 2ah plus h squared plus 2 minus a squared minus 2 all over h. Those 2's cancel, the a squared cancels, and that's 2ah plus h squared over h. And I can go a step further here. I can say that this is equal to, I can pull out an h there, 2a plus h times h over h. And if h is not equal to 0, I can cancel these h's. So it's 2a plus h if, sorry, not a, but h is not equal to 0. In general, it's h over 2a plus h over h, which wouldn't be defined if h is 0. But if h is not 0, this is just 2a plus h. And for the most part, this difference quotient will concentrate on its value when h is not 0. What is this when a is 2? And let's assume and h is not equal to 0. Well, when a is 2 and h is not equal to 0, this is equal to 2a plus h, which is 2 times 2 plus h, which is 4 plus h. Now we don't have a particular value for h there, so we just leave it as it is. We just carry it around as an h because we don't have a particular value for h. What about f of a plus h minus f of a over h when h is 0.1? Well, I know here for sure that h is not 0, so it's 2a plus h. And now I don't have a value for the a, so I just carry it around. That's 2a plus 0.1. What if I have a value for a and a value for h? Well, then I know that this is 2a plus h because I figured that out over here. And when a is 2, that's 2 times 2, and h is 0.1 plus 0.1, that's 4.1. So when I have a concrete value for a and h, I certainly have a concrete value for this, but this doesn't just hold when a is 2 and h is 0.1. This holds for any a in the real numbers and any h not equal to 0. So this is a general formula. I get a general formula depending on a and h. In fact, it's a function of two variables, a and h. And it gives me a particular number whenever I plug in a particular value for a and a particular value for h. Let's try calculating the difference quotient for this function, and of course you should try to answer these questions and then look at the videos which give you the solutions later. Actually, we'll put this on the next video.